Okay, this is the video for CPE 301, design assignment number 6. This is using I2C communication off the Mega 328P. Okay, let's do the usual. Let's walk through some code. Okay, so this design assignment basically is just an example of implementation using using I2C communication. Synchronous serial communication on a half duplex form. It's basically integrated circuit communication, as we all know. So to walk through this real quick, I want to point out some stuff. We use a couple of different libraries. Number one, these are some that were provided by the class to be able to go through and communicate and set up some, mainly set up the I2C, and then it's also some I2C related to the specific module, right? The MPU 6050, which is basically like an acceleration and gyroscope monitor device. So really the important thing is going to be the few libraries here. Let me point that out. Let's go. So the library sets up a couple of important stuff. It's like being able to start, write, read, and the most important, actually read, acknowledge. Like basically the way that I2C works is that we set up this process between communicating between the master and slave devices. So the master, acting as the main role, basically sends command lines out to specific addresses that are assigned to this device. In this case, this is going to be the MPU, and then the MPU just reports back. So we, as the master, we basically start the communication, determine which direction we'd like to have some, write, and then we actually want to have stuff read back to us or acknowledge to us what we receive. So it's just the acknowledge commands, receive commands, and then also being able to write specifically to the registers of that device using these specific I2C command lines. So basically these are filled up. If you go into the main, this is just the header file with the function calls, but if you go into the C code, it goes through the process of what each of these contains. So okay, in connection to that, right, we have the actual MPU file. So this whole file is simply a layout of the register locations inside the operating system of the device itself, inside the the embedded system. So a couple of important ones. Let's see if we can find them. There's some configurations. Their locations. We actually we'll define locations, then write to those locations to determine the values we want, and then our outputs, which are here. So these are all the acceleration output types, high and low bytes. So they're actually 16-bit. So you have to make sure you converge on first the high, and then it'll actually immediately report back the low, depending on the settings. So you do your acknowledgments to say, hey, I reserved the first 8, then the next 8. So, and we'll see that same thing as well. So X, Y, and Z acceleration, and then X, Y, Z in the gyroscope that's internal to the device itself. So, okay. I'm trying to think of, there's also a temperature sensor and a couple different features and stuff like that go along with the MPU itself. It's actually pretty powerful for the little guy. Okay, going to the main C code, using those libraries and using these these commands in over serial communication. Basically, like as we change these values over the synchronized clock cycle between the two devices, we get commands out. So placeholders. It's probably just, I want to go to the main. So there's initialization, writing stuff, setting up the configuration of these registers, setting up the ranges, right, between 2Gs or 2000, depending on which one you're looking at, and that'll actually end up determining your value that you use for some of these conversion later as well, right here. Okay, let me do this one. So basically our main code does our initialization for all these. This is for writing and make it look a little cleaner. Does our UART initialization, the I2C initialization, and then the MPU's initialization. And then we call the get reading function, meaning we basically go to the process of, okay, let's point to the registers in the MPU, and then let's start the highest register in this case, which is going to be X, and then pull values from it. So here, where we basically say, hey, I want to start writing, I want to start from here. I want you to basically start pulling stuff starting at X out, high bit, and then start reading from it at that point. And if I just keep doing the acknowledge in the I2C commands, it'll keep dumping the next register file, or the next 8 bits basically related to that value. In this case, we've got, I'm ORing these two together. I'm like putting these two 8 bits together into one single location like this. So I should say appending. So this is the first, the high bit, and then this is the low bit, or the low 8, high 8, for X, and this is the same thing for Y and Z, and then we'll do the same again. We'll move through, and it recognizes to move to the next location, a register location, which is gyro, Y, and Z, over and over again, and basically just loads those in, and then obviously we have to do our conversions. So those conversions are actually done or shown from the data sheet, depending on which sensitivity selection you use on the device, then you would change these values relative to that coming out. And then we just print it in serial, and prints are a nice little kind of formatting we attempted to do. It's not fantastic, and then just repeats this function every 1 second. So now let's run it, okay, and then we'll go to the visualizer and just see him printing. Had some data earlier, but let's clear it out. And we're writing. Okay. Oh, there we go. Okay, so here we are. So this is just printing over and over again these values. So, and this is relative to the internal setup. So basically, it does like an internal configuration of the sensors to confirm that they're okay, and then sets you running. And those are some of the installation commands if you read through. So this is the board. Look at that, and it's really easy, right? We have these two I2C command lines: the signal clock, and then the actual data pin or the data line. So normally you'd have to set this up and have to put two 10K resistors across both of these, held high or whatever as a part of that. As a part of that input, so you actually get that the signal to come out clearly. But in this case, the development board actually contains those internally. So anyway, so we can go here and rotate this. A point I'm actually going to make too, we'll see here in a sec, I'm probably going to shake it to the point where it gets it to stop. It has this weird, we can't figure out what's going on, but like for some reason, like if you change like angle of the board, move stuff around like too quickly or too fast or something, it causes complications. I still can't figure out what that problem is in the code. So anyway, but it is printing like we need to. So we'll take this, we'll rotate it. So as you can see, our values are changing up there. So I rotate that one direction. So like this, now it's like this. Okay, rotate it up a little bit more. Going really slow right now to just see changes iteratively over time, so it looks good. But you can see it changes. You can change these scaling. I think that might also be in connection to our problem, is that our scaling might be too small, and so large iterations may cause problems. Oh, okay, I didn't kick out yet. Still just rolling this guy around, basically. You see it, notice the stuff. Okay, so if I move it too fast, if I go like this, you'll notice that it might kick out. Oh, so it's moving good. Oh, I didn't do it this time. I don't know if it likes that or not. That's funny. Oh, there we go. Okay, finally kicked out. Stopped like that. So, don't know what does that. It's kind of finicky. There's probably something in the code, maybe a timeout of some kind, or like an overload. It ends up just telling it to shut down or go in reverse mode. So, anyway, so there we go. Looks good. Okay, and that's design assignment 6. Thanks for watching.